Hello and good evening, everybody. Good evening, good day, wherever you are. I hope you're all doing great and welcome to the Ask Abhijit show. It's been a long time since we did an episode that's dedicated solely to science and physics and all of that good stuff. So, before we go, as is usual, let me greet you all. Let's see who all is there on the live stream. I can see Gakusai, Forum, Karan Nalavat, Baby Cheeks, Tanish Kumar, Lelouch, Mao Zedong, Amisha, hello, Atul, Sarvesh, Totan Chaudhary, Pratik Vora, Marisha, Dios Pitra, Yogi PM 2029, Anvit Shetty, Daka Hero, Adel Kodzer from South Africa, hello, Niharika, Kaka, Rajesh Joshi, Megdeep, Sachin, Pratik, Shashank, Baby Cheeks, Harry, Anvit, Gaurav, who else is there? Madan Lal, Ram Devra, Tejas, Daka Hero, Pratyush, Nitin, Harshal, Geopolitics Junction, Megdeep, Shashank, Harry, Gakusei, Shagun, Tanmay, Soham, Chetan, Pritam, Sudhir, Preksan, Ritik, SG, Samarth Acharya, hello, Random Skull, Raju, Chigi Charlak, Curious Prabhat, Jay Dikshit, Madan Lal, and so on and so forth. Everybody, hello. I will not be able to greet you all individually. Priyanka, Ayush, Harshil, Akshat, and so on. Welcome all, and thank you so much for being on this live stream. So, I'm going to take questions that you all have asked in the comments because typically in a live stream about science, I've always seen that if I take questions from the live chat, a whole bunch of other questions get introduced, like history, geopolitics, and whatnot. So I'm going to keep it clean. I'm going to take only science questions from the comments that you all have asked in the comments. So with that said, let us begin with the questions from the comments. All right, where are we? Okay, this is by Prathamesh. What is Aurora borealis? What is the significance? Does it only happen in the northern regions or anywhere else? Aurora borealis. It's been in the news of late, hasn't it? There have been these solar storms, geomagnetic storms that the Earth has been facing the brunt of the past week or so. And auroras have been very visible in various parts of the world. Auroras were visible from northern India, from Ladakh. Can you imagine that? I haven't heard about such an occurrence in my living memory. Auroras visible from India. So, what is the aurora borealis? Is it a phenomenon that only occurs in the northern hemisphere? Not so. That's not quite the case. There is something called the aurora australis as well, which is visible from the southern hemisphere, from the South Pole region. Now, what is this phenomenon? It's essentially the northern lights, the southern lights. You see lights shimmering in the atmosphere. It's typically green. You also have blue, you also have pink, and you also have various other colors. But it's typically the major color that you typically see is green. So, what causes this magical display of shimmering, waving light of various colors? It is the interaction of the Earth the Earth's magnetic field and the atmosphere with the solar wind. So then we have to understand what the solar wind is. The solar wind is plasma that is emitted by the sun on an ongoing continuous basis. The sun has an atmosphere, let's say. I mean, there is a region. If you go towards the sun, then you will reach a region where the sun becomes denser than water. But the sun has various layers, and one of the layers can be called the you could consider it to be the atmosphere of the sun. And there are various phenomena that exist over there. The sun has a very powerful, really powerful magnetic field, and you can see the magnetic lines of force in terms of the solar prominences and all that. And the sun ejects millions of tons of plasma uh, per second, I guess. And what is plasma? It is essentially bits and pieces of hydrogen atoms, essentially free protons and electrons. That's what solar wind is. That's what the plasma is. So all of this is emitted by the sun in all directions. That's one phenomenon that happens all the time. Then you have coronal mass ejections, which are these loops of matter that come out of the sun's surface, and sometimes these loops break off depending on the magnetic field activity. And then there's this massive amount of solar material that's ejected in a certain direction. And if it is coming towards the earth, then well, that causes various uh, phenomena. So you have the solar wind, you have coronal mass ejections, and then you have solar prominences, uh, and you have the emission of various kinds of radiation, typically very high energy radiation, gamma radiation, visible radiation, ultraviolet radiation from the sun, and so on. So now, when the solar wind uh, comes towards the earth, then the earth itself has a magnetic field which is way weaker than the sun's magnetic field. And these charged particles, because they are charged, they will interact with the earth's magnetic field. And you will see that these particles generally are dragged or are pulled by the magnetic field, the earth's magnetic field, towards the polar regions. So this constant stream of charged particles, plasma, it converges in the polar regions because of the magnetic field of the earth, and then it hits the earth's atmosphere at various heights and various speeds. And that's what causes this glowing display of light. So when uh, this solar wind interacts with the earth's atmosphere at, let's say, around 300 kilometers above the surface, it will give you a certain kind of light. Sometimes it will be blue, depending oxygen at which altitude, what kind of interaction is there, that gives you different colors of light. Nitrogen also. So I think oxygen at 100 kilometers above the Earth's surface, if it interacts with the plasma, solar wind, it gives off green light. Somewhat higher, about 300 kilometers, it's blue light, and nitrogen gives off various colors. And the same thing, the same phenomenon happens at the South Pole, in the South Polar regions as well. But when there is a massive amount of plasma coming in because of know, uh, augmented solar activity, then you may see these displays of light even at the southern, I mean, at the latitudes that are closer to the equator, and which is how we had the recent phenomenon where we saw auroras from northern India, from Ladakh. So that essentially is the aurora borealis, aurora australis. Because of the interaction of the solar wind, this plasma, with the atmosphere of the earth, and it happens near the polar regions because of the interaction of this plasma with the earth's magnetic field. The earth's magnetic field drags it and pulls it towards the polar regions, where it starts impacting the atmosphere of the earth, and that's what causes the phenomenon. Hope that explains the matter. Next question. Okay, long question. I am Ayushi, listening to you since age 16. Now I'm 19. Thank you so much. I really appreciate that, Ayushi. So the question is, with exponential development, advancements in science, medical science, technology, I wonder if will we see a time in the future where death will be optional, and will that choice be of privilege? As there is a great shift in perception of death, now it is being approached more like a technical problem and discussed seriously among elites and scientific communities. Billions are being spent on healthcare and longevity, with instances of ultra-rich individuals investing their longevity and doing whatnot. Throughout the ages, almost all parities, probably only death has been an equalizer, but now not even that. I wonder if we are really heading towards dystopia, and that too, not just in one sense. Do you see it incoming? Eager to know your take. Okay, we are in my the way I see it. based on whatever information is available in the public domain. I think we are very far, as of today, from making death optional. Okay. uh, I mean, people are doing research, biological research on telomere lengthening and various other telomerase enzymes that will cause telomere telomere lengthening and all that, and various other kinds of research are being done cognitively, also brain wise, and and so on, to delay aging, to reverse aging, and so on. But I think we are way, way, way far away from any of that becoming actually, controllable, and actually delaying death, prolonging people's age. I mean, what's the average lifespan across the world? I would imagine it will be around 75, 80. If you can extend that by even 5 years, that's going to be a major breakthrough. We are nowhere close to that happening right now, the way I see it. In the future, you may, there could be advances which could delay aging and delay death. So let's say you're able to add 20 years to a human being's lifespan through some treatment, through some medical treatment. So a person who would typically live until the age of 80, they will now live to 100. Or maybe you can extend the average lifespan to 120. Even that does not make death optional. You People will eventually die. I mean, eventually, um, the end of life will happen. And I don't see any technology that is currently being considered or developed or even imagined that could actually completely take away the possibility of death, because there are factors that go beyond simply keeping the body alive. Okay. D- Death is caused primarily by aging, and everything deteriorates and so on. Let's say you extend someone's lifespan, and let's say you make it 200 years, for example. Can the human brain sustain itself for 200 years? Okay, the human mind, because that's a certain finite amount of space in which you have all this data that goes in, and it can only handle, let's say, 80 years or 100 years of memories and experiences and data. You go beyond that, you're going to have to start overwriting data, and you may lose old memories, and eventually you may forget who you actually are. You may forget the first 100 years of your life if you live to 200. Who knows? That may also happen. So I don't think that's something that's desirable. Uh, so I don't see this sort of dystopia emerging anytime soon. We're going to have AI, we're going to have all these wonderful advances that are going to transform our life. But I don't think we are at the position, even close to it, where death becomes optional. But yes, if you look at science fiction writers, I mean, I've read all kinds of science fiction from the 19 from the what 18th century onwards. The first science fiction novel is considered to be Frankenstein by Mary Shelley, and I've read science fiction for over the ages. And if you look at science fiction written in the 1950s and 60s, in 1940s, it's very, very optimistic. And today, all science fiction is pessimistic. It's all dystopian. So it looks like technology is dragging us towards a dystopian kind of future, especially the big corporations that control technology and release it and implement it, and so on and so forth. So yeah, you could see a dystopian future emerging, but I don't think death has we are anywhere close to making death optional right now. Okay, Swapnil Mishra says, did space time have a boundary at the Big Bang singularity, given that the universe is believed to have had zero size at that time? What were the boundary conditions at the beginning of time? Good question. Did space time have a boundary? So, we're talking about the Big Bang singularity. First of all, the Big Bang is the event that gave birth to the universe. That's the best theory that we have in cosmology. And this Big Bang event was not an explosion, it was an expansion of space time. It happened roughly 13.8 billion years ago, according to the best information that we have. Some researchers would say that it could have been before that, maybe double the time. But the mainstream theory is that it happened 13.8 years ago. And the universe is believed to have been a vanishingly small point at the time, what we call the Big Bang singularity. Now, what was this Big Bang singularity? A singularity, from the perspective of general relativity, is a position. It is it is a location. It's Let's talk about time. You go back far enough in time, and the entire universe the curvature of the universe becomes infinite, and the density of the universe, matter and energy density of the universe, becomes infinite. That's your Big Bang singularity. Now, in mathematics, singularity, when you have a singularity, it essentially means you're dividing something by zero, which is unphysical, and it actually indicates that your theory is there is some flaw or deficiency in your theory. So maybe there was something else, maybe not a singularity, but the best theory that we have says that there was a singularity, which then expanded, and it gave rise to the universe that we have today. So the expansion happened in different, let's say, stages. I mean, we look at it from the perspective of stages, but overall it was just a smooth expansion. Not entirely smooth. You had inflation, which happened a fraction of a second after the birth of the universe. You had the decoupling of the forces and all that. So that's what happened. Now, what was the geometry of the universe? What was the shape of the universe? Was there something beyond the universe? Was there a boundary between the universe and what is not the universe? We don't know. We don't have sufficient data. uh, there are these theories. There is a theory put forth by Stephen Hawking, the late Stephen Hawking, and Hartle, which says that there was no boundary. And it says that when you go back closer and closer to the moment of the Big Bang, then time itself becomes fuzzy and it takes on spatial, spatil, the aspect of space. So there's a theory like that. And so basically what I'm saying is that the physics of the very early universe is very poorly understood. To properly understand the physics of the very early universe, let's say in the first second after the Big Bang, you would have to develop a quantum theory of gravity, which incorporates quantum effects with general relativity. Because when the universe was that small, all the physics was quantum physics, right? Because that's the ultra microscopic domain, the quantum domain. So, and at that point in time, you would have a unified force, a single force, which then decoupled and other forces decoupled and the symmetries broke, uh, and so on. So you would need to develop a working, a viable quantum theory of gravity, which includes general relativity as well as quantum mechanics, quantum field theory, and we don't have that right now. And because of that, the physics of the very early universe is very poorly understood. First of all, because we don't have sufficient data. We have data. What data do we have? We have the cosmic microwave background radiation, which came much later on, which was created, which emerged out of the universe, out of space time much later on. So overall, we have very little understanding of what really the conditions were like at that time, and that's why it is not a question that we have clear answers to, but it is a very fascinating question, and it is questions like these that fascinate physicists and drive research forward. So yeah, there you have it. Okay, Happy Faces 228 says, "What is space time? Why space and time are merged together, and how can we perceive time as the fourth dimension?" Okay, what is space time? We understand the universe, we visualize, we perceive the world, the universe in three dimensions: length, breadth, and height. Right, the three dimensions. That's what we see, and we can also perceive the passage of time. Our perception of time is kind of vague and fuzzy, but we see the universe, see our life and the events that happened around us in a chronological linear fashion. So that is what gives us the impression and the understanding that time is passing. So time is something we have a fuzzy understanding of. And when it comes to relativity and quantum mechanics, time is looked upon as a linear parameter. It happens, it's a linear, and in a linear parameter. In quantum mechanics, time is an external classical parameter. It's not something that emerges out of quantum mechanics. And when it comes to relativity, uh, well, let's talk about special relativity first, the easier part of relativity. There are two kinds of relativity: special relativity and general relativity. So in special relativity, uh, the interval between two events has the parameters of distance as well as time. Okay, so you can see that time as well as distance are included in the space time interval in special relativity. Okay, and in general relativity, what Einstein did was that he constructed a four-dimensional view of the universe, in which we have three dimensions of space and one dimension of time. So it's a four-dimensional view of the universe, a mathematical view of the universe. And what general relativity tells us, okay, the Einstein equations, it's a very, very rigorously tested theory. It has withstood all tests and it is correct. So what it tells us is that there are four dimensions, three of space that we can see, and one of time that we perceive, and time goes linearly. Well, it looks like it goes linearly. And matter exists in this four-dimensional stage. So whatever happens in the universe, whatever events and happen in the universe, they are played out on this four-dimensional stage called space-time. Three dimensions of space and one dimension of time, and every object, everything in the universe, every star, every planet, every human being has a world line, which is a path on the four-dimensional stage of space-time. And the presence of matter curves space time, not just space but also time, all right? And the curvature of space time tells matter how to move. So that's the theory. I mean, that's the best I can tell you in words. To truly understand physical theories, you have to look at the mathematical equations, but for that you have to understand the mathematics. When it comes to general relativity, you have to understand tensor calculus and all that. But that's how one could describe space time. So space and time, we see that they are merged together. We see that in special relativity itself, in the space time intervals between events. So space and time, these two parameters, they come together in the equations. And then in general relativity, it goes in a whole different to a whole different level, essentially. Happy Faces again says, how can we imagine the curving of space by massive objects? So the standard view that they will give you is that space time is like a two-dimensional sheet or fabric, and you put a ball a ball on space on that fabric, and this fabric of space time is curved. That's how they'll show it. So you were visualizing some kind of curvature of space and maybe time also in two or maybe three dimensions. But here is a better way of looking at it. Let me put this image on the screen. Check it out. So this is a more three-dimensional view of how the presence of matter curves space time. We're actually seeing this in three dimensions, not four dimensions, because the human brain is not able to visualize, is not capable of visualizing a four-dimensional universe. We can only see three dimensions. We can't visualize four dimensions. At least I can't. Okay, my brain isn't that great. I can only see things in three dimensions. So imagine this was four-dimensional, then it would kind of work like this. So that is how you can visualize or imagine the curving of space by massive objects, and also how the curvature of space bends the trajectories of these massive objects, the way they move. All right, there we are. Next. Okay, this is by Pratyush Rai. I've always heard stuff like the physics used in our day-to-day life is quite different from the physics observed at the quantum level. Subatomic particles follow a mere probability function. Phenomena such as quantum entanglement have been seen, where a single particle can exist in not quite in two different places. That's not how it works, but I'll come to that. What do you think is the reason for such an enormous difference in the physical state of bodies that coexist in the same universe but have to follow different laws of physics? Well, they don't follow different laws of physics. They follow the same laws of physics. But we see the macroscopic world, the ordinary world that we inhabit, differently. And the quantum effects aren't that apparent at all in the ordinary mundane world that we live in. But when you zoom in, like a hyper zoom in, then you will see atoms and molecules and subatomic particles like protons, neutrons, electrons, and quarks and whatnot. And these particles, they obey the rules of quantum mechanics. So at some stage, at some scale, the ordinary world that we are familiar with, this ordinary world emerges from the quantum scale, from the quantum world. Okay, it does emerge from the quantum world. So how does that happen? Yeah, that's the question. So what kind of laws do quantum objects follow or obey? You have like you said, entanglement, but entanglement doesn't mean that a particle is in two places at once. It means a pair of particles that are described by the same wave function can be as far apart as you want, maybe a light year, maybe 100 light years, but certain some of their properties are correlated. So if you look at one particle, you'll immediately know what is the corresponding properties, what are the corresponding properties on the in the other part of the other particle, no matter how far away it is. But it doesn't mean there is faster than light communication or any such thing. So that's a little difficult to explain, but that's not how it works. I'm sure you've watched the some science fiction series like the three body problem or whatever, in which they're communicating through entanglement. That's not how it works. That is so wrong. That is so wrong. So entanglement means two particles. You can have more, but let's say you have two particles that they are described by the same wave function, and some of their properties are correlated. Let's say, very silly and very straightforward comparison or illustration. Let's say you have a pair of gloves. A pair of gloves. Okay, I have a pair of gloves. One left-handed glove, one right-handed glove. I put one in one box, another in one box. I send one of the gloves to London. I send the other glove to Moscow. Okay, and I myself don't know which glove is in which box, which one has gone to Moscow, which one has gone to London. Now my friends in Moscow and London, the moment they open the box, they will know exactly which box is there in the other place. That's kind of how entanglement works. So at the subatomic level, you have entanglement, you have superposition, in which particles exist in multiple states. In a superposition of multiple states, there is the observer effect, the collapse of the wave function. The moment there's a measurement or an observation, the wave function collapses. That is something you don't see at the classical level, at the macroscopic level. uh, there are all kinds of other phenomena that are very there is quantization, obviously, there is wave particle duality. So particles can behave like waves as well as particles. The electron can behave like a wave. It can also behave like a particle. Photons, which are massless, can behave like particles as well as waves, and so on. And you can prove this using experiments like the double slit experiment and all that. But such phenomena are not visible at the classical level, at the macroscopic level. But these macroscopic phenomena emerge from the quantum level. So what happens, see, for example, and it's because of the wave it's because of the wavelength. See, the wavelength, the de Broglie wavelength of a particle is the smaller the particle is, the larger the wavelength is. And the larger the particle is, the smaller the wavelength is. So quantum phenomena are become apparent, and they take precedence over classical phenomena when the wavelength is significantly large. So photons have different wavelengths depending the color of the light. This is blue. You're seeing blue photons emerging from this fabric here. You're seeing orange photons from behind. So the light, it tells you the wavelength, kind of, if you know what the wavelength of what color is, and so on. But this ball, it also has a de Broglie wavelength, but it's extremely small, and that's why the quantum effects are not apparent. And when I mean, you can even solve the Schrodinger equation for the Earth Moon system or the Sun Earth system, and what it will give you is gigantic quantum numbers, principal quantum numbers, and all that, and energy levels. So the larger the quantum numbers and the larger the energy levels, the less apparent the quantum effects are. So that's what it is. And then there is the correspondence principle. Niels Bohr came up with the correspondence principle, which essentially says that the larger the quantum numbers and the larger the energy levels, etc., the less apparent the quantum effects are. So because of that, what we have is that the ordinary mundane macroscopic world, it actually is a quantum world, but we don't see the quantum effects because they are not visible enough. But there are certain objects, certain phenomena that are purely quantum at the macroscopic scale. Bose-Einstein condensates. Most of us obviously will never see them, but those are macroscopic quantum objects, phenomena, macroscopic quantum phenomena. That's one. Neutron stars. Well, we don't really get to see them, but those are quantum objects, gigantic nuclei, essentially atomic nuclei. Then you have crystals. You see this? This is an ordinary quartz crystal. It's a crystalline object. The properties of this crystal are purely quantum mechanical. Okay, the hardness, the shape, the angle of at which light reflects, the colors, all of this is purely quantum mechanical. This is a purely quantum object. This is a macroscopic molecule, essentially. So there are certain quantum effects that we see, are visible. We may not realize it, but overall, everything that exists at the classical level, the macroscopic level, emerges from quantum mechanics, from the quantum world, via the correspondence principle. All right. Happy faces again. All right. When do you see quantum computers being available commercially? Okay, quantum computers. There is a lot of talk about quantum computing in the past 4 5 years. I think Google had announced. I mean, companies like Google, Microsoft, and whatever else, they are investing in quantum computing. They're developing quantum computers, and I think in 2018 or 2019, Google or somebody announced that they had achieved quantum supremacy, which means that their quantum computer was able to do a certain task which a classical computer simply can't do. A standard computer simply can't do. Well, understand first of all that even your regular laptops and what all these computers are based, they operate based on quantum mechanics. At the end of the day, those chips and circuits and the everything that happens in that, it would not work without quantum mechanical technologies like semiconductors and so on. The gates on on a circuit, in a computer, in a regular computer, they operate because of the semiconducting property that they have, and that's a quantum property and all that. But quantum computers are about using quantum mechanical phenomena and controlling those, such as superposition, entanglement, and all that, by creating qubits, quantum bits, which are superposed bits instead of classical bits, and then you manipulate those quantum bits to perform calculations and so on. That's how quantum computers work. So right now we are in the early research and development phase of quantum computing. I would say that maybe in the next 5 or so years, 5 or maybe 10 years, you would see hybrid computers becoming available. They'll be very expensive, and only some corporations or governments will be able to afford them initially. So these hybrid computers will have some quantum component as well as classical components, and they'll be used mainly for cryptography and for drug discovery, molecular analysis, protein analysis, things like that. But those will be initially hybrid computers, because it's quantum computers. They are very delicate. You need to have an extremely cold temperature within, in which you create the superpositions and all those quantum computing bits, qubits. And qubits are very fragile. They need extremely cold temperatures. The presence of any heat, warmth, would destroy the the superpositions and entanglements, decohere the quantum effects, and then that's the end of it. And even if it's slightly warm, then you could have errors creeping into the computations. You would need correction codes, and those are still in the process of development. So I think the best quantum computers right now can superpose, I don't know how many qubits, maybe a handful of qubits, maybe 100 or so qubits, maybe 1,000 qubits. But for a proper quantum computer, you would need millions of qubits working together at the same time. I would say 5 to 10 years, you would have hybrid systems emerging. Then between 10 to 20 years, you may have better, more robust, more powerful quantum computers coming, but it becoming accessible and available to everybody. I mean, a quantum computing laptop, 20 plus years easily. So that's how I see it happening. It's a very new technology. It's a nascent technology, but yeah, it has very powerful future applications if the technology can be developed to make it work properly, reliably, and efficiently. Okay, Ad Guru Prasad says, how do computer processors understand the programs or any command? Okay, computer processors are called central processing units. Now this is a very deep computer science question. I will try and give you an overview. So central processing units, right? The CPUs. These are the brains of computers, and they execute the instructions and they perform the calculations that essentially run programs, execute programs, and that's what happens. Now, how does this happen is the question, right? So, a CPU, a central processing unit, has a number of components. There is the ALU, the arithmetic logic unit, which performs arithmetic and logical operations. There is the control unit, the CU, which decodes or which directs operations by fetching, decoding, and executing instructions. So, fetching instructions from where? From somewhere, or from your hard drive, or from a flash drive, or whatever. You fetch the instructions, you decode the instructions, okay, because the instruction will be written in some high level language like Python or C++ or whatever. You to break it down, you decompile it to the machine language level, and then you to execute it sequentially. Then so that you have the ALU, you have the control unit, then you have registers in computers, which are small and fast storage locations for temporarily storing data and instructions, okay. Then you have a cache, which is a very small and fast memory that stores frequently accessed data and instructions, which essentially helps to speed up the processing. So that's the basic components of computers, of CPUs. Now, how do CPUs understand programs and how do they execute programs? So, like I said, computer programs are written in high level languages, Python, C++, and whatever else it is, and they have to be translated, they have to be converted and decompiled into the machine language, which the CPU can understand. And what is machine language? Machine language is essentially binary code, ones and zeros, right? We've all seen those ones and zeros, but that's what the machines understand. So these high level instructions have to be decompiled and converted into the ones and zeros. And then there is the fetch, decode, execute cycle. That is the cycle by which, the process by which CPUs operate. It fetches, the control unit of the CPU retrieves or fetches an instruction from the computer's memory, from the RAM. It decodes that, it translates the fetched instruction into signals, zeros and ones, which can be understood by the CPU's other components. Then it executes the instruction. It has already been decoded. Then you take it to the various parts of the CPU. Let's say you take it to the ALU, the ALU, to perform a calculation or whatever. And then there are instructions that is part of the architecture of the CPU. That is the instructions that the CPU understands and it can execute. Every CPU has its own architecture, its instruction set architecture, which defines the machine language instructions and it can understand and execute. So you load a program, which is loaded from storage. Let's say you have a game that you want to run, so it's going to be on your hard drive, or you can insert some kind of storage device. And so the program is loaded into the RAM. Then the CPU uses the program counter to keep track of all the instructions, the next instruction to fetch. It is done sequentially in extremely fast, in very quick time. Then the fetched instruction is placed in the instruction register. It is decoded and it is decompiled into the ones and zeros. Then it is then that it will then signal the ALU and other components of the computer to perform whatever operation has to be performed based on that instruction that has been fetched. Then the results of the operation are stored somewhere. They're typically stored in a register, or they can be written back to the RAM of the computer, and so on. So there are addition instructions, there are fetch instructions, there are decode instructions, there are execute instructions, and then you have these gates, logic gates, and gates, not gates, or gates, XOR gates, and whatever, which are all used in various ways to perform various operations. And that is kind of how it works. It's a very, very, very high level overview that I've given. It's fascinating. Computer architecture, computer programming, how the computer works at the very basic low level. That's how computers work. So that's how computer processors, uh, they operate by a combination of fetching instructions, decoding them, and executing instructions in a cycle. And this happens over and over again. And the CPUs understand programs through machine language instructions, which are encoded in the architecture of the CPU. And that's kind of how it works. All right. Okay. Okay. Dungar Singh Chauhan says fasting for how long kills cancer cells in the body? Okay. So this is not very well understood. We know that there is a correlation between cancer and sugar, which is glucose. So when you eat sugar, let's say you eat candy, or you eat honey, or you eat a chocolate, or you eat a sweet dessert, that is going to be broken down in your stomach into glycogen, into glucose. Okay, glucose essentially. The glucose will enter your bloodstream, and then there's the insulin thing and all that. I'll not go into the insulin part, but the glucose is a very fast burning, very readily accessible fuel for the cells of the body. So the cells of our body, they can use two kinds of fuel. One is uh, glucose, and the other is fat. So let's say you are chubby fat, you've got plenty of body fat, then if you don't eat sugar for, let's say, 4 days, 5 days, then the body will run out of the sugar reserves, glycogen reserves, and then it will have to move to start burning fat. And that is a process called ketosis. And ketone bodies are created out of the breakdown of lipid cells in your body, and that is what serves as the fuel source for your cells. So glucose, it is a very explosive, athletes need glucose for those explosive movements like sprinting and all that. If you look at the way Usain Bolt, the world record holder over 100 meters and 200 meters, how he used to train, he would always, as part of the training and performance cycle, he would always take sugar or something sugary just before a race, because that gives you that explosive burst of energy which sprinters need. If you're a long distance runner, it doesn't really help that much, because you need to sustain your run for a long distance, 10 kilometers, or if you're a marathoner, 30 whatever kilometers. In that case, fat can be a more efficient fuel source. Now the point is this: uh, there seems to be a relationship between cancer cells and sugar. And if you stop eating sugar or carbohydrates, because that's the same thing essentially, then the body has to go into ketosis after let's say 3 or 4 or 5 days. It goes into ketosis. There's no more glucose to burn, and that could essentially possibly starve off cancer cells. And the process of fasting, it is the best way to enter ketosis. Instead of you stopping to eat sugar and carbohydrates and just focus on protein and fat, which could take time, you just stop eating for 3 or 4 days. That will ensure that by the time day 4 is over, your body has entered ketosis. And there are various symptoms that some people experience. Some people have keto flu or whatever. What this process does, if you fast for 4 days, it is believed, I think it's been proven, perhaps, I'm not really sure, you can look it up, that your immune system regenerates itself over this 4-day fasting period, and you enter ketosis. And what also happens is a process called autophagy, which means that all the dead, dying, senescent, damaged cells in the body are all destroyed, and their spare parts are reused for creating new cells. So if you have precancerous cells, or maybe even cancerous cells, those could be destroyed, and that's good. So that's why fasting intermittently once in a while was a good thing. But there needs to be more research. I'm not sure if there has been established a clear link between fasting and killing cancer cells. But yeah, I mean, hopefully you don't have cancer. Hopefully nobody has cancer. And so fasting regularly, maybe once a week or maybe once a month, 3 4 days, that could actually be a great way to ward off the possibility of ever getting cancer. But yeah, I think more medical research is needed to conclusively prove this. But yeah, it's been part of Indian tradition, fasting, either weekly or once in a month or twice in a month. And there's always good reasons for old traditions. Okay. Geopolitical Dube asks a question about physics. That's great. Astrophysics. So the question is, why is there no square, triangle, or other shaped planet in the galaxy? Why is it always circle or spherical, round shaped planets? Can you explain the science behind this? Yes. So it's because of the action of gravity. Okay. Gravity is the weakest of the four forces. What forces do we have? We have the strong nuclear force, we have the weak nuclear force, we have the electromagnetic force, and these three combine to become the electroweak force. And then you have gravity. And gravity is the weakest of the interactions. Okay. Uh, but yeah, gravity is what shapes the universe at the largest scales. Now, let's say you have a collection of gas. Okay. And there is an over density somewhere, then because of self gravitation, this entire gas cloud will start coalescing together. It will start moving together in a certain direction, clockwise, anti-clockwise, in whichever plane of motion. And that is how protostellar clouds are formed, which lead to the birth of solar systems with a star at the center. Okay, so it's because of the action of gravity that this happens. Now, in any stellar system or solar system, you're going to have some hard, solid material, which is going to be very less compared to the mass of the star itself, but it's going to give rise to the formation of planets. Okay, and when you look at small masses, let's say we have asteroids, right? These are all irregularly shaped. Why is that? Because they are too small for gravity to really take over. But when you have large enough objects, okay, with large enough mass, then gravity will take over, and it will ensure that the most efficient shape possible is created. And the most efficient shape possible is gonna be a roughly spherical shape. When it comes to gaseous planets like Jupiter, Saturn, and all that, they are mostly smoothly almost spherical, not exactly spherical. I'll come to that. In the case of larger planets like the Earth and Mars and Venus and so on, I mean, they are not as large as the gas giants, much smaller, but even here the force of gravity has taken over, and broken down the various components of the planet into a roughly spherical shape. Now, because the planets are rotating, there is going to be an equatorial bulge, and you will see this more pronouncedly with gas giants like Saturn and Jupiter. Even the Earth itself has an equatorial bulge. So not every planet is no planet essentially is perfectly spherical. But it's because of the action of gravity, which wants to create the most efficient shape possible, that this happens. So that's why if you have a planet with the mass of the Earth, you try to make it into a triangular shape or square shape, you will see that over time the action of gravity is going to turn that into a spherical shape, a roughly spherical shape. And the longer the time goes, the more spherical it gets. That's what happens. It's because of the force of gravity. Swapnil Mishra says, why do we experience time in a linear fashion in the universe rather than exponentially or logarithmically? If the universe were to stop expanding and start contracting, would the thermodynamic arrow reverse, creating a decrease in disorder over time and leading to backward time instead of forward time? Okay, so why do we experience time in a linear fashion in the universe rather than exponentially or logarithmically? Um, Experiencing means it is something that it's something to do with our perception of the universe. Now we know that there are certain clear laws of the universe. We have general relativity, we have quantum mechanics, quantum field theory, and so on. We know that in general relativity, time essentially is the fourth dimension, and in that you can actually go backward and forward in time, mathematically at least. Okay, when it comes to quantum mechanics, time is an external parameter, and once again, it's a linear parameter. So everything we see about the universe, you see that time is linear. So it's just the way the universe is, and our perception of time is also linear because we see events happening sequentially. We experience events happening sequentially, and we have never experienced events happening backwards in time. So that's just the way it is, that we experience it in a certain fashion. Maybe the universe could be different, and maybe our brains and our cognition and our cognitive abilities are not that advanced that we could perhaps experience time differently. But yeah, the laws of physics are such that time is linear. Maybe in other universes, if they do exist, you may have exponential or logarithmic time. But in this universe, it seems to be completely linear. Now, the other question is also interesting. If the universe were to stop expanding and start contracting, would the thermodynamic arrow reverse, causing a decrease in disorder over time and leading to backward time instead of forward time? So, time is one of the biggest mysteries in the universe. What is time? What causes time? Is time an emergent property of the universe, or is it just an illusion that we perceive? Well, it seems to be connected with entropy. Entropy is a measure of disorder in any system or in the universe overall. The universe is a system, and it has a certain amount of disorder. And so, any system that has a lot of disorder, randomness, is a high entropy system. And any system that has a very high amount of orderliness is a low entropy system. I would imagine that some of the lowest entropy systems in the entire universe would be the human brains, because they are so orderly, right? And so full of information and data in a very, very systematic manner, stored in a very systematic manner. Uh, so what you will see is that, according to thermodynamics, the entropy of any system increases over time, and that seems to create the uh, thermodynamic arrow of time, because in any system, entropy can either stay the same or increase. It can never decrease, right? So that seems to cause that forward arrow of time. So it seems to be perhaps connected to entropy or related to entropy. Now, let's say, like you say, the universe at some point in time, because of its geometry or whatever reason, stops expanding. Right now, the expansion of the universe is actually accelerating. So the universe is expanding, and the acceleration of the universe is actually the expansion of the universe is actually accelerating. But let's say in the future the universe reaches its maximum expansion point, which means that you have a big crunch situation, perhaps a cyclical universe or a big crunch universe, and then the universe starts contracting, going back towards the initial singularity of the Big Bang. Okay, so what happens then? Does it mean that the thermodynamic arrow reverses? Does it mean that the entropy starts decreasing? Well, we don't quite know for sure. In such a situation, in such a case, such a scenario, does the entropy of the universe start decreasing? We know that the volume, the size of the universe will start decreasing, but does it mean that it becomes more orderly over time? And does it mean that the time starts going backward? And I'm not sure that that could quite be the case, because even if you take a closed system with a gas within it, okay, and you squeeze it, and you make it smaller, you shrink it, the gas will get hotter for sure, but will it become more orderly? I don't think so. Okay, it may actually become more disorderly. So it may not quite be the case that if the universe starts contracting, it will become more orderly, the entropy will decrease, and the thermodynamic arrow of time will reverse. So yeah, but these are all hypothetical questions. We don't quite know what will happen, if this will even happen or not. But very interesting questions, and that these can give rise to very interesting thought experiments in physics that can help us unravel some of the big mysteries, including time, which is one of the biggest mysteries. Okay, Anvay Sharma asks a similar question. The universe is growing, expanding right now, and time is moving in the outward or forward direction. So when the big crunch happens, will the universe coil inwards, and will the arrow of time be reversed? I already answered that. And everything that happened in the past will happen again. I don't think that's quite the case. I don't think that everything will happen in reverse if the universe starts contracting. I think its evolution will continue in a certain direction, according to the laws of physics. I don't think it will start. All the events will start playing out in reverse order again. I don't think so. Because the memory of everything that ever happened might be stored somewhere in the universe. We don't know about that. Whether the memory of something, of everything that ever happened, may be stored somewhere. There is no physical process or law that we are aware of that would be storing the memory of everything that ever happened, a record of everything that ever happened somewhere. You have holography theory that talks about the surface of a sphere of the universe may possibly encode all the information within, but then where is that information stored outside? I mean, that question isn't answered when it comes to this question. So I don't think the arrow of time would be reversed. I could be wrong, obviously, because we don't know. We've never experienced such a scenario. But that's speculation and hypothetical. And according to the laws of physics, as we know them, that arrow of time will not be reversed. What exactly is information? Well, what is info? That's a good question. Well, it depends on the context in which you're asking me. Are you asking me about information from the context of information theory, or from the perspective of quantum theory, from the perspective of black holes, from the perspective of computer science? So if you're talking about computer science, then information is just bits and bytes, ones and zeros, right? Like we discussed some time ago, ones and zeros stored on the computer's hard drive or in memory or in RAM or whatever. That is information from the perspective of computer science. From the perspective of quantum physics, information is the various states of of the system. So let's say you have a system. Let's say you've got a square box in which you have a gas. Okay, let's say you have hydrogen and helium mixed together, and let's say you have n number of hydrogen atoms and m number of helium atoms. Okay, and it's a mixed gas, and they are interacting in some way or the other. So in this case, information is the state of each of these atoms or molecules. Okay, the quantum states. Let's take atom 1 of hydrogen. What quantum state is it in? Is it in the ground state? Is it in the excited state? So all of these various data points taken together is quantum information. Are certain atoms entangled? Are there superpositions of some kind, and so on and so forth? All of that is quantum information. uh, in information theory, information is correlated with entropy. I'll not go into that. It's pretty complex. I don't know how to explain without mathematics and so on. From the perspective of black hole physics, information is again the quantum states of everything that goes into the black hole. So a black hole is a classical object. Okay, a black hole is, from the perspective of general relativity, it's a classical object. It is a very simple object from the perspective of general relativity. It has only three properties: mass, charge, and angular momentum, and that's it, nothing else. So it has a certain amount of mass. It may or may not have a certain amount of charge, and it may be spinning or rotating or not. So mass, charge, and angular momentum, and all the properties of a black hole can be described by using these three parameters. These three parameters, and other properties are derivatives of these three parameters. For example, entropy is a function of the surface area of the event horizon of the black hole. Uh, the radius of the event horizon, if it's a Schwarzschild radius, then it is 2 mg by c squared, and so on. I'll not go into the details. So a black hole, from the general relativity perspective, is a very simple, straightforward object. But it is, let's say, it is a black hole that is accreting gas. So it's accreting hydrogen and helium and whatnot gas. I mean, all of these gas atoms and molecules are quantum objects, and they all have quantum information within them. It's also, uh, once light crosses the event horizon, even light is not cannot escape the black hole. Light also has information, polarization, in what direction are the electric and magnetic fields pointing, the polarization information. So all of this quantum information is going into the black hole. It's going inside, right? Now, once it goes inside, what happens to the information? Does it get destroyed? Does it get scrambled? And all that is the black hole information paradox. Because black holes have temperature, and they radiate the radiation, Hawking radiation, which could be particles, antiparticles. It has a black body spectrum, and these particles that are emitted, uh, do they encode the information that went in, and so on. So that is the black hole information paradox. So it if you want to answer what is information, you have to understand which context, from which perspective you want to understand: computer science, black hole physics, quantum mechanics, philosophy, whatever. So there are lots of different ways of explaining what information is. Also, information theory. Okay, two questions. Smart Buys 3118 says, recently India has successfully tested phase 2, the fast breeder stage of thorium reactors. How far are we from phase 3 and successfully developing it completely? Akash Rocks Akash Rocks says, Do you see thorium based power plants in the near future in India? However, scientists cracked the formula to do so, or do we still have a long way to go? Secondly, do you see lithium based electric vehicles dominating the future? Do we have a good amount of lithium reserves, and also reserves of other critical minerals on Earth to support this change? Okay, so let's talk about the thorium angle, the phase 2, phase 3 of the Indian nuclear program. India has successfully tested one thorium reactor, the fast breeder stage thorium reactor. How far are we from entering phase 3, developing successfully? And what is the future of thorium based power plants in India? So, India, as I'm sure most people would know, hopefully, that India has a three-stage nuclear power program. India has a three-stage nuclear power program. This was which was developed in the 1950s, 1960s, somewhere around that time, by Dr. Homi Bhabha. So this program was designed. It was created. This plan was created to efficiently use India's resources. So India has limited uranium resources. India has to import uranium from other countries, but India has abundant thorium reserves. India has the highest amount of thorium anywhere in the world. Okay, so, considering these factors in mind, the limited amount of uranium that we have, and we have to import uranium from outside, and we have so much thorium. So, then considering that, considering all of this, the three-stage program was developed. So, the first stage is the pressurized heavy water reactors. Okay, so these reactors use pressurized heavy water. And they use natural uranium as fuel. So the objective of these reactors is to generate electricity and also to produce plutonium 239 as a byproduct. Okay, so in these pressurized heavy water reactors, there heavy water, which is deuterium dioxide. No, it's D2O, deuterium. So D2O is used as the moderator and the coolant. Okay, so that is the first stage, the pressurized heavy water reactors. So these reactors use uranium as natural uranium 238 as the fuel, and some of these uranium atoms absorb neutrons and they get converted into plutonium 239. 238 plus 1 is 239, and they generate electricity and also simultaneously generate plutonium in the spent fuel. So that is the first stage. We have those reactors. The second stage is fast breeder reactors. So in fast breeder reactors, you are using a mixed oxide fuel, which is a blend of the plutonium 239 and the natural uranium. So you're not using simply uranium, you're mixing it with plutonium 239, and that is the fuel that you're using in these fast breeder reactors. So the objective of these reactors is to breed more fuel than you are consuming, and also to generate electricity. So the fuel is going to be a mixture of uranium and plutonium, but it's going to generate even more plutonium than it consumes, and it's going to generate electricity. And in such reactors, you're using liquid sodium as the coolant. Okay, so that is a fast breeder reactor, and that is what has been tested. So India was supposed to have entered the stage 3 of this three-stage program a long time ago, but for whatever reason, we are now entering phase 2, and one of these reactors has apparently been tested. Okay, so we are not yet at the thorium stage. You understand? We are still at the plutonium stage. We are now building fast breeder reactors that use a mixture of uranium and plutonium, that fuel, to generate more plutonium and also generate electricity. That's where we are. The third stage is where you have advanced heavy water reactors, and you're using thorium to breed uranium, which is fissile and which can be used as a fuel. So it uses what's called a closed fuel cycle to efficiently use thorium as the fuel. Thorium is not fissile, but it can absorb neutrons and it becomes uranium, which is fissile. So in the reactor, thorium is Th232. It absorbs neutrons. It becomes Th233. Then it undergoes a beta decay, and it subsequently decays to uranium 233. And this uranium can be used as a fuel. It can sustain the reactor's operation and ensure a continuous fuel supply. So that is the three-stage program. We are still at stage 2, which is not yet the thorium reactors. Okay, so the deal is that India has the world's largest reserves of thorium, which makes it a very attractive resource for long-term energy security for India. So this three-stage program, it its objective is to reduce dependence on imported uranium and to leverage domestic resources, which is thorium, and so on and so forth. So that is the deal. So that is where we are. The first stage has already been successfully implemented with numerous pressurized heavy water reactors, which are operational in various parts of India. They're generating electricity. They're also generating plutonium, which is great. Okay, stage two. We are entering stage two now, and we have to demonstrate the viability of the Indian fast breeder reactor technology. Okay, and then when we have sufficient number of fast breeder reactors, then we will start entering doing the development of advanced heavy water reactors for which can use thorium as the primary fuel. So that is where we are, and that's the deal. So I don't know for what reason the program is delayed and so on, but I'm sure we have the means to get to stage three, hopefully soon enough. You need funding, resources, government support, and all that, but yeah, should happen. Avinash Kale says, in which direction did the Big Bang happen? I'll tell you what, the Big Bang happened right here. And wherever you're sitting or watching, it happened there also. Because the Big Bang was not an explosion, it was an expansion of space time. And the entire universe was squeezed into essentially just a very tiny, infinitesimally small point, which means everything that we see in the universe, all the stars, all the galaxies, and whatnot, galaxy superclusters, all of that was squeezed into that little point. Okay, so everything came out of that little point, which means that Big Bang happened everywhere. It was not an explosion; it was an expansion. So yeah, here is where the Big Bang happened. Wherever you are, there also it happened. As simple as that. Okay, Happy Faces 228 says, how did Newton discover the law of gravitation, since it's almost impossible to see any force between small masses? Very good question. So which when was Newton born? When was he alive? You can look it up. I don't remember the dates. So here's the deal. When Newton was a student, at that time, certain information about the movements of planets and stars was available. Some aspects of the laws of nature were understood. For example, from the experiments of Galileo Galilei in Italy, in Pisa, and so on, we knew that we knew that gravitation exists, and we knew about the law of inertia. We knew that masses fall at the same speed, and so on. So inertia was known, the falling of masses towards the attraction, the force of attraction, the gravitational force was kind of known at least. And Kepler's laws of planetary motion were known. Three laws of planetary motion. Uh, so Kepler used data that was acquired by his by Tycho Brahe. It is believed that Tycho Brahe got this data from India. But anyway, that's a different story. So Kepler's three laws of planetary motion were known. The way planets, you know, move around the sun in elliptical orbits, and the way they move, and so on, all of that. So this information was available by the time Newton started thinking about what became the Newtonian law of gravitation, right? So it is said, maybe it's apocryphal or whatever, that he was sitting under an apple tree and an apple fell on his head, and then he had this brilliant flash of inspiration. We don't know if that really happened or not, but what the insight that Newton got was that the falling of objects like apples on the earth is, it could be the same, it could be governed by the same laws that govern the movements of planets and stars in the skies. So Newton came up with the first unification of forces. Okay, uh, the laws that govern the movements of the celestial objects are the same laws that govern the falling of objects on Earth. And at that time, it was known that the further a light source is away, moves away from you, the dimmer it gets. I think everyone knows that, but it follows an inverse square law. So the intensity is proportional to the inverse square of the distance between you and that light source. That was also kind of known. So Newton then applied that to gravitation. That maybe the strength of the gravitational interaction or the force is proportional to the inverse of the square of the distance between two objects. And that's how he came up with the famous equation F is equal to G, capital G, m1 m2 upon r squared. Okay. And so it was a flash of inspiration, of insight. And he said that if it is true, then you should be able to develop to develop the equations of the Kepler's laws of motion, Kepler's law of planetary motion from this. So he used his theory of fluxions, which is now called calculus, which he had somehow discovered at the time, and he was able to get the three laws of motion, Kepler's laws of motion, from his theory of gravitation. So that's kind of the manner in which the discovery of the law of gravitation by Newton happened. It was a flash of insight that he got, but it was also based on the speculation initially that the same laws of motion govern the falling of objects on the earth, that govern the movements of objects in the sky, and so on. So I guess that's how Newton was able to discover the law of gravitation and then use calculus to prove that this law of gravitation is the basis for the Keplerian laws of planetary motion. Okay, Purple Rose 0301 says, how do celestial bodies stay afloat in space if space is empty? Space is empty. So how do celestial bodies stay afloat? You're talking about floating bodies. Where are they floating? They're floating in something, right? So here's the thing. They aren't really floating. The universe is a stage in which things exist. Energy exists, matter exists, objects exist, massive objects, massive massless objects, particles. All of this exists on this stage. And this stage is a four-dimensional stage called space-time. And all the dynamics of all the objects, the way they move, the way they are situated with respect to each other, and so on, all of that is governed by general relativity, and which is gravity. Okay. And inertia. So inertia is Newton's first law of motion. Any object will keep on moving in a straight line, or will either stay at rest or keep moving in a straight line unless it is acted upon by an external force. I think that's roughly how we could say it. So that is the law of inertia, Newton's first law of motion. And then you have general relativity, which is the curvature of space-time. Mass causes space-time to get curved, and the curvature of space-time tells mass how to move. And essentially, this is what is responsible for the various locations and positions and movements and dynamics of celestial objects. So they're not afloat somewhere, floating in the air. They're out there in space time. Essentially, they're out there in space time. Now, is space empty? That's again another question. Well, space is not really empty. It is bathed in the very faint afterglow of the first light of the universe, the cosmic microwave background radiation, which is just about 2.7 or so degrees above 0 Kelvin, minus 200 something Celsius. You can look up, do the conversion. Okay. So space has this faint afterglow. It is bathed in this faint afterglow, the ancient photons, the first light of the in the aftermath of the Big Bang. But then you also have quantum fluctuations all over the place, and that's what quantum field theory tells us, and that has been proven to be true. So you have quantum fluctuations, virtual particle antiparticle pairs being generated and annihilated spontaneously all the time, all over the place. And then you have other things. You have trace amounts of hydrogen gas in space. So it's not entirely empty. It's not quite a perfect vacuum. There's always something or the other in there. But yeah, that essentially is the way it is. Okay, Arjun Sinha says, what made the galaxies of different types? Okay, why do galaxies come in different shapes, in different types, like spiral galaxies, elliptical galaxies, irregular galaxies, and so on? So, yeah, that's a great question. So, galaxies have existed for a very long time. I think the James Webb Space Telescope has shown us that the first galaxies emerged in the first half a billion years after the Big Bang, which maybe the first 300 million years after the Big Bang. So yeah, that's been a big surprise. So galaxies have been around for a very, very long time. and galaxies emerge out of the formation of stars. So you have a tremendous amount of gas, okay, and that gas acquires a center of its own through the process of self gravitation, and then it starts spiraling, and then you have these star forming regions where new stars are born, and over time this entire thing becomes a galaxy, and somehow it acquires a central supermassive black hole. And such a galaxy that forms in such a process, self gravitation and so on, that typically acquires a spiral shape with arms, okay. So the our galaxy, the Milky Way, is a great example of a spiral galaxy, and our neighboring galaxy Andromeda is also a beautiful spiral galaxy, okay. So that's how a spiral galaxy is formed. Now, these elliptical galaxies, how are they formed? Typically, elliptical galaxies are formed by the merger of two or more spiral galaxies, or other galaxies. So when you have a spiral shape, you have two spiral galaxies that are going to come together and merge. Some people would call it a collision. It's actually a merger. There's no real actual physical collision of anything. There's too much empty space in a galaxy for anything to really collide. So it's going to be a merger. It's going to be a gravitational dance of billions of objects. The Milky Way and Andromeda are going to merge in this manner in the next 5 or so billion years. Billion. Long time. We're never gonna see them. Never gonna see it. But when this happens, the two spiral galaxies, they get distorted, they dance around for a few billion years, and eventually the entire thing settles down, and it settles down in the shape and form of an elliptical galaxy. So elliptical galaxies are typically formed through the merger of two or more regular galaxies, maybe spiral galaxies, or galaxies of any other kind. So that's how elliptical galaxies are formed. What about irregular galaxies, weird shaped galaxies? So the universe is always moving, but it moves over a very long time period, billions of years. So when you see an irregular galaxy, it's a galaxy that has experienced some kind of massive gravitational phenomenon that has disturbed its shape. So it's either two galaxies in the process of merging together. There are these two galaxies called the mice, right? The mice. You can Google it. Or there has been some other kind of gravitational event that has distorted it out of shape. So typically, galaxies, when they're first born, would generally be born in having a spiral shape. Then when galaxies merge, they become a larger elliptical galaxy. And when galaxies collide, I mean merge, or are in the process of merging and dancing the tango with each other, that's when all these arms are distorted and torn apart and stars are flung in various directions. That's when you have irregular galaxies. So that is essentially the answer to your question. Okay, Swapnil says, how did the fundamental principles. How did the fundamental principles and laws of physics before chemistry and biology that govern our universe originate during the Big Bang? How are these laws of nature and physics so consistent and persistent, appearing like controlled variables? Yeah, or the fundamental principles and laws of physics that govern our universe and are responsible for everything we see, these laws and principles originated during the Big Bang and the subsequent evolution of the universe, of the cosmos. Okay. So the Big Bang was when the original, what we believe to be singularity, Big Bang, primordial singularity, experienced perhaps a spontaneous expansion or whatever caused it. We don't know what caused it. Okay. So the universe began as an extremely hot, extremely dense point, approximately 13.8 billion years ago, and then it expanded. And as it expanded, it started cooling, and it underwent a series of phase transformations that set the stage for the formation of the first fundamental particles and the formation of the fundamental forces. We know of four forces: the strong nuclear force, the weak nuclear force, the electromagnetic force, and the gravitational force. So the first second of the life of the universe itself is a tremendously long epoch. The first fractions of a second, in that time the universe was in a very, very highly dense energetic state. Okay. And then you have a period of cosmic inflation, an exponential superluminal expansion of the space. So this process of inflation, it helped homogenize the universe and set the initial conditions for the development of the physical laws that we know so well. Now, in the early stage, there was the entire universe was governed by a single law. That's what is believed. Okay, we don't know. A single unified force, super gravity or whatever you want to call it, the grand unified force. So that is what the universe was governed by initially. That is what we believe. And as the universe expanded and cooled, the symmetry broke spontaneously, and we eventually got the four fundamental forces that we observe today. So this spontaneous symmetry breaking is a key concept in understanding how the different forces and particles emerged. For example, you may have heard of the Higgs boson, the Higgs mechanism, which explains how the various particles acquire mass through interactions with the Higgs field. So that's what is believed to have happened. Now, the laws of physics that we know, they are formulated in the form of mathematical equations, and they describe the regularities and patterns of the universe. They describe the behavior of the fundamental components of the universe. We have the Einstein field equations of general relativity. We have the Schrodinger equation, wave mechanics, quantum mechanics. These are all based on various symmetries and conservation principles. So this mathematical consistency that we observe everywhere in the universe, as far as we can see, the laws of the universe are the same everywhere. And this mathematical consistency is what ensures that these laws apply apparently universally. Okay, so, and all of this is influenced by symmetry and the invariance and the transformations of various laws and so on. And we have conservation laws like the law of conservation of momentum, of energy, of mass, which ensures that everything remains consistent in the universe. And then you have the standard model of physics that provides a comprehensive framework for understanding the three forces that we kind of understand: the electromagnetic force, the weak force, the strong nuclear force. we don't quite we're not quite capable of yet thus far of fitting gravitation into the standard model, but that's where you have it. Okay, and then general relativity takes care of gravitation, and all of this has been experimentally validated. The universe seems to be homogeneous and isotropic on the largest scales, which means that the physical laws should be the same everywhere in all directions, which kind of makes them appear like they are controlled variables. And we have evidence that comes in from the cosmic microwave background radiation, which tells us that the early universe had a nearly uniform temperature and density, with perhaps some regions of over densities and all that. So it's a long explanation, but that's kind of how it is. When you ask very very fundamental questions as to how did these principles and laws of physics emerge and originate, we don't quite have the answers. For that, we need to develop what is seemingly impossible: a grand unified theory, a theory of everything, the equation that answers all your questions. But we still don't have it. So we are still kind of groping in the dark and grappling with these questions. But these are the questions that fascinate us and drive theoretical physics research forward. Shashank Garg says, what's the difference between dark matter and antimatter? Okay, let's talk about antimatter first. Okay, what is antimatter? Antimatter is a very straightforward thing. It's a type of matter that is composed of antiparticles. An antiparticle has the same mass as its regular particle of ordinary matter, but it has the opposite electric charge and it has the opposite quantum properties. So it is not just charged in an opposite manner, positive to negative, but the quantum properties are also the opposite. And when a particle and its corresponding antiparticle meet, they annihilate, and they release a tremendous amount of, well, a very properly measurable amount of energy in the process. So for example, we are familiar with electrons. Yes, electrons, electric shocks. So electrons have antiparticles called positrons. So the positron has the same mass as the electron, but instead of a negative charge, it has a positive charge. So that's a positron. That's the antiparticle of the electron. Now we know of protons. Protons are positively charged. They are components of the nuclei, right? So the proton has an antiparticle called the antiproton. So the antiproton has the exact same mass as a proton, but it has a negative charge. The neutron is also a component of the nuclei of various atoms apart from hydrogen. So the neutron, as we know, is a neutrally charged particle. It has no real charge, no charge. Even the neutron has an antiparticle called the antineutron, which once again is electrically neutron, but it has the opposite baryon number. Okay. Then neutrinos have corresponding antineutrinos with opposite lepton numbers. So, like I said, when particles and antiparticles come together and they meet, they annihilate each other in a burst of energy, typically photons. And these are typically high energy photons, gamma rays, and and it could be also particle antiparticle pairs. Uh, so yeah, that's how it goes. And antimatter can be produced in particle colliders like the Large Hadron Collider, particle collisions and accelerators, and also in certain types of radioactive decay spontaneously. And yeah, that's what antimatter is. Now, what is dark matter? Dark matter is nothing, it has nothing to do with antimatter. It is that mysterious 25% or so of the universe that we don't understand. If you look at the total mass energy composition of the universe, we see a lot of stuff out there in the universe, don't we? We see stars, galaxies, nebulas, quasars, pulsars, neutron stars, whatever, all that. You add all of that together, all of that matter together in the universe, that makes up only 4% of the mass of the universe. 4%. That's it. The rest of the universe is unknown. It is dark. We only understand 4% of the universe, and that too, not very well. Okay. So then there is about 25 or so percent roughly, which is dark matter. And the rest, about 70, 71%, maybe 69%, is dark energy, which is even more mysterious. I'll not go into that, dark energy, because you didn't ask me about that. So, what's dark matter? Dark matter is most likely some kind of particle or particles which interact only gravitationally. Some physicists will say that dark matter can have the weak interaction. Well, for me, that's not dark matter, because we can detect neutrinos. I know that most of them pass through us. There are trillions of solar neutrinos that are passing through my body right now every second, and they typically don't interact at all with the ordinary matter. But yes, we can still detect neutrinos, which means that they are not dark matter. From my perspective, dark matter has to be purely gravitating matter, some weird kind of particle that we are not familiar with, or family of particles, or class of particles. So it's quite likely there is dark matter in this room with me, and it may be passing through me right now, and it will interact even more weakly than neutrinos, way more weakly than neutrinos, or it is essentially impossible to detect. But we can detect its presence through gravitational lensing and the dark matter halos that are known to exist around galaxies and so on. So it is some kind of matter that we don't know, that we are unable to understand. Probably some kind of particle or particles. Maybe it has something to do with primordial black holes or microscopic black holes, or perhaps bound states, stable bound states of microscopic black holes, quantum bound states, perhaps. Who knows? So, yeah, that's the difference between dark matter and antimatter. Anvay Sharma says, what are tachyons? Well. You remind me of ECG Sudarshan, the great physicist who should have got at least 3 Nobel Prizes, but he got none. Will not go into that story, but I think I believe it is he who first put forth the proposal of tachyons. So tachyons are a hypothetical class of particles that travel faster than light, and you cannot bring them down to light speed or below light speed. They only travel faster than light, which means they have imaginary mass. Their mass is imaginary. Okay. You can calculate that using the basic equations of special relativity. I'll not show the calculation because we are just talking here. So a tachyon, a particle that can only travel faster than light, would have an imaginary mass. What's an imaginary number? It's a number that involves I, the square root of -1. Okay, so that essentially is what tachyons are: imaginary mass. And they if tachyons exist, you would have causes before effects, and that's why it looks like they don't exist. But who knows? So yeah, that is in brief what tachyons are. Okay, Akshat says, if the observable universe is 90 billion light years wide in diameter, how come it's just 13.8 billion years old? Is good question. Yes, there is something called the cosmic horizon or the observable universe. And if the universe is 13.8 billion years old, as all the best data tells us, then the furthest that a light ray can travel should be 13.8 billion light years, correct? Right? But we observe light coming from about 45 billion light years away. That tells you that the radius of the observable universe is about 90 billion light years. But the radius should just be 13.8 billion light years. Why is it so that it is actually much larger than that? Well, the answer is very simple. It's because of the expansion of the universe. The very fabric of space-time is expanding. And what's causing the expansion, we don't quite know. Maybe it's dark energy that is doing it. But because the universe has been expanding, that's why we see light coming from so far away, even though it is just at most 13.8 billion years old. And how do we know that it has expanded that much? Because that light is redshifted. We see the light being redshifted. We know the characteristic spectral lines in various elements, and you see the same spectral lines, but they are shifted towards the red end of the spectrum. That's redshift, which tells you that that light has come from it has had to travel so much more because the source is moving away from you. It's the Doppler effect, essentially. If you have blue shift, as in the case of light coming from the Andromeda galaxy, then those spectral lines will be shifted towards the blue end of the spectrum, which means that it is coming towards you, and all the wavelengths are squashed. Frequencies are squashed together, and that's why these frequencies are higher, blue shifted. So that's how we know that all this ancient light that's coming towards us is red shifted, highly red shifted. Some of it is totally infrared, and that's why we have to use instruments such as the James Webb Space Telescope, that is something that only detects infrared wavelengths, because they are so tremendously red shifted that they are no longer visible. So yeah, so that's why the observable universe is 90 billion light years in diameter, even though it's just 13.8 billion billion years old. It's because of the expansion of the universe, which is accelerating. Okay, Bhabo Pradhan says, if our universe expansion accelerates, if its expansion is accelerating, so how does our universe get an external force to accelerate? Well, we don't know what it is that's causing the expansion. That's a good question. A very straightforward solution to this problem is that somebody from outside the universe is imparting some external force which is causing the universe to expansion to accelerate. So maybe the universe is like a balloon. This is a tennis ball, but like a balloon, and somebody from outside has this pump, and they're pumping in more air, and that's why they're expanding. Well, that's a very straightforward. It's called Deus ex machina in fiction. A plot device that solves any problem. It's God, or it's some aliens from outside who are providing energy to the universe to make it expand and and accelerate the expansion. Well, that sort of solution can solve any problem that you have, but we want to look for a mathematically and physically logical and consistent solution to this problem. So it could be what we call dark energy, which makes up about 70% of the mass energy of the universe, and we don't know what it is. Is it a fluid? Is it a force? What exactly is it? It seems to permeate everything. It should be here, but it's completely unknown. And maybe it is that is uh, footing the bill of the energy bill of the expansion of the universe. So yeah, we don't have the answer, but maybe the answer may lie in the solution to the mystery of what dark energy is. Okay, Archana Tyagi says, please explain Hawking radiation and how will black hole vanish after trillion of years. Yeah, black holes are weird objects. I wish I had a black hole in a lab. Then I would really be able to, get data, new data that could help throw light on what gravity actually is like at the quantum scale. But we know that black holes most likely exist. We have seen objects that look like black holes. We know that there's a black hole at the center of the Milky Way. We know there's a black hole at the center of this of whatever other galaxy we recently took a snapshot of, the Event Horizon Telescope. So we know black holes exist. They have been observed. Now, what we find, what Stephen Hawking demonstrated using a semi-classical calculation, is that black holes actually evaporate. Okay, they lose mass. So we know that a black hole has an event horizon, and anything that crosses that horizon will never be able to return from the black hole. It will eventually fall inwards towards what's believed to be the central singularity of the black hole. And as you fall inside, you get all distorted, twisted out, and the spaghettification happens, and not a good way to go, unless it's a gigantic black hole. So that's what you have. But now, at the boundary of the black hole, at the boundary of the event horizon, we I referred to some time ago about the uh, quantum field theory effect of the spontaneous creation and annihilation of particle and antiparticle pairs. And that is something that kind of violates the Heisenberg uncertainty principle. But the particle antiparticle pair again spontaneously annihilates itself before the delta t condition is violated in the uncertainty principle. So it's fine. Okay, so let's say you have particle antiparticle pair that is formed right outside the event horizon boundary, and this antiparticle particle pair it's formed like this, and one particle falls inside the event horizon, can never come back, and the other one goes in the other direction. So essentially, the black hole, through its gravitational field, is footing the energy bill of creating this particle antiparticle pair, this virtual pair, which was supposed to spontaneously annihilate itself, and then no energy would have been lost. But what happened is that one particle escaped and one was absorbed, which means that the black hole has actually lost mass. The particle that fell inside is considered to have negative mass, and the particle that goes out is considered to have positive mass. So if you're an observer at a distance, it will look it will look like the black hole is radiation is coming out of it because of this effect, and this is called Hawking radiation. So this tells you that the black holes have temperature because radiation is coming out. It is black body radiation, okay, completely random radiation that's coming out of black holes. So black holes have a temperature, and the temperature depends on the inverse of the mass of the black hole, inverse of the square of the mass of the black hole, or the mass. Look it up. Look it up. Okay. So that tells you that the larger a black hole, the colder it is, and the smaller a black hole, the hotter it is. If it is hotter, it means it will radiate faster. So the hotter a black hole is, the faster it radiates, and it eventually ends up exploding. Boom. So black holes end their lives in explosions. But when it comes to large black holes, supermassive black holes, they are so cooled that they are colder than the interstellar space. They are colder than the cosmic microwave background radiation temperature, which means they accrete over time, which means they are essentially immortal. They will never die. Their lifetime is longer than the current age of the universe. So yeah, that is what Hawking radiation is, and that's why some black holes are apparently immortal. Their lifetime is apparently longer. Not apparently, you can calculate and demonstrate it's longer than the current age of the universe. They're going to be around essentially forever for all intents and purposes. So yeah, trillions of years possibly. There you have it. Okay, Anvai Sharma says whenever an event happens or time passes, a part of the information is either stored in our memory or in some other digital format. Okay, so is it possible to reconstruct the entire event or thing because it exists but in our conscious memory and not in the external world? You see, our memory is fallible and it is not perfect. Unless you are one of those super geniuses who have a photographic memory, but most people, our memory is very, it's vague, it's imperfect. We have recollections that are not entirely accurate, and the longer the event longer ago the event happened, the fuzzier our memory is. Okay, and let's say I observe this ball bouncing and up and down, but do I know the exact composition of the ball, every single molecule, every single quantum state? What is the air pressure inside? How many air molecules are there inside? What is the oxygen, nitrogen, carbon dioxide, helium, etc. composition of the gas inside the ball? I have no idea. So how do you reconstruct the whole thing from just my vague memory of the ball bouncing around? So that's why it is not possible to do that. Okay, the human brain is marvelous, but it's a very small object, and it simply cannot contain the entire record of what happens. Forget about the entire universe in our own vicinity. I don't know what's happening behind me right now. Maybe there's a fly or a mosquito flying around. I don't know, right? So there you have it. So lots of events happen without any conscious observer observing them. So you cannot reconstruct all these events. All right. Okay, Swapnil says, what triggered the Cambrian explosion during the Paleozoic era, in which there was an explosion of animal life? Where did all this new genetic information come from in a geological instant? So the Cambrian explosion happened about 500 million years or so ago, 540, roughly half a billion years before today. Until that time, the entire world, the entire uh, landscape of life was very straightforward, multicellular and unicellular life forms. But the Cambrian explosion was this tremendous, creative outpouring of genetic experiments. And it's the first time you have in the fossil record animals with hard shells and exoskeletons and endoskeletons. Uh, so what caused it? We don't quite know what caused it. Maybe there was an abundance of oxygen. See, initially, in the initial phase of the first phase of life on the planet, oxygen was a poison, and there was this great oxygenation catastrophe that killed off about 90% plus of all life forms on the planet. That is more than 3 billion years before today, or roughly around 3 billion years before today. But later on, oxygen became the gas that life forms need to stay alive, to survive. Even today, for us, if you breathe in too much oxygen or pure oxygen for a long time, it kind of acts like a poison, and it's not a good thing. But yeah, so around 540 million years before today, maybe there was an increase in the oxygenation level of the atmosphere, maybe an increase in the oxygen concentration of the oceans as well, and maybe that caused this sudden outpouring of so many new kinds of species. Maybe the amount of calcium and phosphate and all that in the oceans also increased, which enabled animals to develop endoskeletons, exoskeletons, and all that. So that's what the fossil record tells us. We have the Burgess Shale in England, in the British Islands, and so on. So we see this sudden outpouring of genetic diversity, and uh, maybe it's the first time predatory animals emerged in the oceans, which necessitated that other animals also had to evolve and take evolutionary defensive measures, and evolve in such a way that the predators could not catch them very easily and devour them very easily. So maybe that also was one of the causes of so much diversity emerging. But all those animals that emerged at the time, they are the ancestors of all the animals that exist today, and one of them surely was our ancestor as well. Yeah. Okay, Danush says, thoughts on manipulating telomeres to extend human lifespan. Is it a viable option? Is it ethical to do so? So, in our cells, you have chromosomes, and at the ends of chromosomes, you have telomeres. Okay, these are genetic ends of the chromosomes. And as cells multiply over and over again, the telomeres get shorter and shorter. And that is the phenomenon that is associated with the aging process. So the shorter your telomeres are, the older you are, and the more visibly aged you are, wrinkles and whatnot. Okay, all that. So that's the aging process. So it is believed that if you reverse this, and if you lengthen the telomeres in your cells again, you may get youthful, and you may either stop the aging process, or even reverse the aging process. And there is an enzyme called telomerase that is believed to be that is known to cause the lengthening of telomeres. But there are risks involved in that, because if you lengthen telomeres, it can very strongly give rise to cancerous cells, immortal cells that simply don't want to die. Cancerous cells don't die, by the way, uh, unless the host dies. But you may have heard of the Henrietta Lacks cell line, which is immortal, if you want to look into that. So one of the risk factors is cancer. You play around with telomeres and extending the length of telomeres, you may end up causing cancer. But yes, that is something that is this technology of lengthening. not technology but research into this matter. Telomeres and lengthening telomeres is going on right now, and maybe it could give rise to interesting developments, and maybe people could have longer lifespans as a consequence of that. It certainly is viable. Where I think in the infancy of such research, is it ethical? I don't think there's any human rights concerns or anything. The only risk is that you may end up giving people cancer, so you have to be really careful about that. These days, we know how things have been in medical science, so we need to be a little more careful. So as long as you do it properly and do your due diligence, then it's reasonably ethical to do so. Swapnil says, why do single digit numbers go up to only 9? Why is 10 a two-digit number and cannot be written in a single-digit format? Moreover, why are numbers 0 to 9 shaped and written the way they are? Okay, the shape thing is a historical thing. It all came from the Indian numerals, Brahmi and all that. So we'll not talk about that today. The reason it's shaped like that is because these are Indian numerals that were uh, adopted by the Arabs and then transmitted to Europe. That's how it happened. Now, why do single digit numbers go up to only 9? It's because we use the decimal system, base 10, which is why we have only 10 characters. 0, 1, 2, 3, 4, 5, 6, 7, and 9. That's 10 characters. And then if you want to go beyond that, you need to use two digits. We have the base 2 system, the binary system, in which you have ones and zeros only. So in that numbers become long very rapidly. Then you have other systems like the hexadecimal system, which is base 16, in which you have the digits 0 to 9, and then you have A, B, C, D, E, F. A, B, C, D, E, F. G. Okay, I don't remember right now, but yeah. So that's the hexadecimal system. Then you have something called the uh, vigesimal system, I think. Vigesimal system, which is base 20, in which you have 20 characters. So until you reach 20, you will have a single digit format. So it entirely depends on what base you're using to write your numbers. Base 2, which is decimal, base 2, which is binary, base 10, which is decimal, base 16, which is hexadecimal, base 20, which is vigesimal or whatever. Okay, that's how it is. It's just the way you which base you use. Okay, Indrajit says, what are your thoughts on the primordial black holes? Some papers say that these are micro black holes and they are responsible for dark matter. Also, I wonder how matter was compressed below the Schwarzschild radius to form them, if they exist, or is there some other way? So primordial black holes are believed to be those microscopic black holes that were born perhaps in very large numbers in the very very early universe, in the infancy of the universe, when the universe was so small and so squeezed together that a very small quantum fluctuation would create a region uh, of matter over density, in which the matter was compressed beyond its Schwarzschild radius, and maybe there was an overproduction of micro black holes at various epochs in the very early universe, during the pre-inflation phase, maybe during the inflation phase, maybe during the reheating phase, recombination phase, wherever. Okay, there are several scenarios that point towards a possible overproduction of primordial black holes in the very early universe, in the various early stages of the universe's existence. So that's a mechanism by which primordial black holes could have formed. Okay, now we know that the early universe was very hot and primordial black holes were in this soup of radiation, which means they could have possibly accreted matter over time. And then the universe expanded, became cooler, and then the primordial black holes would have started radiating because they became hotter than the environment. And as we know, like we discussed, the Hawking radiation, every black hole has a temperature. The smaller it is, the hotter it gets, and so on. Uh, so it's possible that some of those black holes born in the very early stages of the universe may still exist today if they were born with a certain kind of amount of mass. Um, if that is the case, then we should be able to detect them. We should be able to detect the end stage explosions of primordial black holes, but we have never seen that. We can detect gamma ray bursts, we can detect other things, cosmic rays, and so on, but we have never detected what seems to be an exploding primordial black hole. Why is that? Does it mean that primordial black holes never existed? Does it mean that they all evaporated long time ago? Or does it mean that they are still tied up somewhere else in some form. Yeah, so that's my thoughts about primordial black holes. They could be responsible for dark matter as a component of dark matter, um, and so on. Maybe if they formed stable bound states, gravitational bound states, in which they don't decay, don't evaporate, then they could perhaps uh, form, be a component of dark matter. There is also the possibility that uh, once it evaporates enough, there's a Planck mass sized particle that's left behind, which is either called a plankon or a cornucopion or whatever, which doesn't decay, which is stable. So that's one possibility, that once a black hole, primordial black hole, evaporates out and it reaches the Planck mass, then it cannot evaporate any further. And then you have these remnants, incredible amounts of Planck mass sized remnants of primordial black holes, which cannot evaporate any further and which are purely gravitating objects. That could certainly be a viable uh, form of dark matter if that exists. But do they exist? We don't know, because it's very hard to detect them, almost impossible using current technology. So there you have it. Dominic says, is it possible to make a spacecraft which can use the plentiful hydrogen available in outer space? So in outer space, in the vacuum, in the supposed vacuum of outer space, you have trace amounts of hydrogen, you have antiprotons, protons, electrons, all of that roaming around, but in a very dilute form. So is it possible to make a spacecraft that can utilize this hydrogen that's out there, all this hydrogen? Well, theoretically, it's very much possible. Theoretically, it's called a Bussard ramjet, which will have a gigantic ram scoop, which is made up of these massive magnetic fields, which scoops in hydrogen in front of the spacecraft over a area of multiple light years, which means that they're gigantic ram scoops. Okay, if it is a circular thing, it's like multiple light years in area, and then that sucks in all this hydrogen, and that serves as the fuel for the ramjet that drives the spacecraft forward. So that's a concept called a Bussard ramjet, Bussard, Bussard ramjet. So yeah, theoretically very much possible, but technologically, is it feasible for us to do that? I think we'll have to become a type 1 civilization or something before that. Okay, Ratna Singh says, please throw some light on asteroid mining and interplanetary human species in the future. Okay, so we are not quite an interplanetary species right now. No human being has ever set foot on another planet. The furthest we've gone is the moon, which is our own satellite. Um, we have human beings in orbit around the Earth on the International Space Station, and various nations have the ability to send human beings into space. Even the Chinese have it. The Indians will also do it in a year or two, by 2026 or something. So that's the best we can do right now. The best we can do technologically is to get to the moon. Now, maybe by 2030s, by the 2030s, maybe by the 2040s, you may have the first human beings on Mars. That's what Elon Musk wants to do. The technological ability to do that will be available to him very soon. The gigantic rocket he is developing. So, yeah, eventually, if all goes well, we will become an interplanetary species. The next place we will go to will obviously be Mars, which is the most logical place to go to. Venus is too hot, too hellish to even think about, unless you want to stay in orbit or in the upper reaches of the atmosphere of Venus. But Mars makes sense. It is smaller, it is more Earth-like, and you could even terraform it over a period of a few centuries, or faster if you use dirty means, and so on. So yeah, humanity could become an interplanetary species in the future, as long as we do things properly and don't have a third world war or whatever. Asteroid mining is much more far-fetched. Theoretically, certainly you can do it. You get asteroids which are rich in various metals and minerals. You know, some asteroids may have more iron than the entire iron uh, ore that's present on our planet. That's also possible. But the thing is this: the asteroid belt between the orbit of Mars and Jupiter, it is almost empty. Okay, it's a tremendously large number of asteroids, but it's almost empty space. There are millions of kilometers between two asteroids on average. It's almost empty space. So how do you find the asteroids? How do you reach there? How do you mine them? How do you bring them back to your planet? It's a tremendous amount of investment, of time, of resources, of fuel, and all that that you have to do just to get the contents of one asteroid back. So eventually, if you have the technology to harness the resource of the whole solar system, then asteroid mining makes sense. But right now, it's far fetched. It's not going to create trillionaires, billionaires anytime soon. At least not for the next century, minimum. Maybe not the next couple of centuries. I could be wrong. I hope I'm wrong, but the way the technological progress is happening, it doesn't look like that's going to happen. So theoretically very possible, but practically impractical from a realistic perspective. Ad Guru Prasad says, uh, artificial rain. Okay, is it artificial rain or something else that was responsible for the Dubai floods? It was cloud seeding. It was artificial rain that caused the Dubai floods because of a freak combination of weather conditions. So, what is artificial rain? How is it created? What is cloud seeding? Cloud seeding is when you create artificial rainfall for whatever reasons by seeding the air above a region with nucleation, with particles that act as nucleation points for the creation of water droplets or ice droplets, which could eventually become snow or rain. So you typically use sodium iodide or sodium chloride or some. I think I can remember sodium iodide, silver iodide, and sodium chloride. These two, and you release fine grains of these, fine particles of these, and these are seeded in the atmosphere, in the air, and they act as nucleation points for the creation of water droplets, clouds, and all that, and then it gives rise to rain. So that's how cloud seeding happens, and that's how artificial rain is created. Now, if you go to the UAE and in that part of the world, you will see that there's a lot of artificial clouds being created. If you are flying over the Arabian Peninsula in the UAE region, you'll see these weird cotton-like clouds that are all spaced out, almost in an even spacing. Okay, and very close to the ground. It's so strange. It's very unnatural. So these are artificially created clouds, and these clouds give rise to rainfall that that is good for them overall because they would like more greenery and more better cooler temperatures and all that. But then what happens is sometimes you have a situation in which various air currents come together, and all these clouds, they are not able to go out, and the atmospheric water doesn't disperse, and that is what can give rise to these freak conditions that create torrential rainfall. And that's what happened in Dubai recently. So this very dry desert area, very arid place, suddenly had tremendous rainfall and flooding, unheard of. So that happened because of cloud seeding and artificial rainfall, and I think even Oman had to bear the brunt of uh, this flooding. Okay, so I have exhausted the 28 or 29 or 30 questions, roughly 30 questions that I had picked. Let me now take a couple of minutes and maybe take some questions from the live chat in case you have any questions. Okay, let's see this question. Sarvagya Sharma says, if a wormhole was to open and everyone on Earth goes to a different universe with entirely different laws of physics, then would we notice the difference, or will thinking process change? I think if we are sucked into a wormhole and transported to a different universe where you have different laws of physics, then we will not function the way we are supposed to function, and that would essentially mean the death of us. I'm not even sure whether it's possible to travel through a wormhole unscathed. Okay, wormholes may not be traversable. In some cases, you would need some exotic matter in the throat of the wormhole to make it traversable. Exotic matter such as matter with negative mass. Ooh, imagine that. Or you may need cosmic strings, primordial cosmic strings, to keep the throat of the wormhole open. But the conditions in the throat could be horrifying for life. I mean, not amenable to the survival of human beings, unless you are in a very strong spacecraft. But then you end up, let's say, like you're saying, in a different universe. Well, you won't survive that. But wormholes from the general relativity perspective, wormholes don't take you to a different universe. They take you to a different location in the same universe. But yeah, there you have it. Okay. Okay. Karan Nalawat says, what is quantum cosmology? So we know what cosmology is. It is about the evolution of the universe, the cosmos. Astrophysics is more to do with the various objects that exist in the cosmos, like nebulae and pulsars and quasars and neutron stars and galaxies and so on. Cosmology is about the evolution of the universe, large scale evolution of the universe and all that. So quantum cosmology is about using quantum mechanics to explain the evolution of the universe. That's a very simple, straightforward, and very brief answer to your question. Okay. See, this is the problem. This is why I don't take questions from the live chat in when it comes to science, because you will have you will have questions about other topics in there. Okay. Um, okay, here we are. Tushar Verma says, what are white holes? White holes are, you can think of, see, we have the Einstein field equations of quantum, of general relativity. Okay. And we have various solutions to these Einstein field equations. So we have the black hole solution, we have the wormhole solution, and then we have white hole solution. So what are white holes? You can think of it this way. You know what black holes are. We all know what black holes are like. People think of black holes as this giant vacuum cleaner that suck everything inside. That's not quite the case. A black hole is just an object which cannot radiate light because the mass is contained within the Schwarzschild radius or the event horizon, all of it. So that's why it is completely black or transparent. Black, actually black. They're like holes in space time. Now, imagine a time reversed black hole. So a black hole, whatever comes in its way, it will suck it in, right? It'll suck it in. If something is coming towards it, eventually it will end up inside the black hole. So from that perspective, it's like a vacuum cleaner. Now imagine a black hole with time reversal. So time is flowing backwards. Then you will see the black hole throwing out stuff outside, right? Instead of swallowing, it will be vomiting stuff, regurgitating stuff. So that's essentially what a white hole is. It is like a time reversed black hole. And when it comes to the objects at the center of galaxies, we don't know whether they are black holes or white holes. I mean, you know, so there are certain tests that one could do to try and figure out whether it's a black hole or white hole, but that's what it is. So a white hole is a specific solution of the Einstein field equations, and it's like a time reversed black hole. Okay, I already took the question about antimatter. What else do we have? Tripped reverber. What's the difference between radio wave signals and laser signals, and how laser signals will be more effective for future communications? Radio signals are modulated electromagnetic waves at a certain range of frequencies. Uh, so they are electromagnetic waves for sure. Okay, and they are at a certain range of frequencies, and there is modulation, time modulation, frequency modulation, all of that. I'll not go into the details of that, but you can look up those concepts if you like. So those are radio signals, a certain specific range of frequencies. Laser. What is a laser? The full form of LASER is light amplification by stimulated emission of radiation. Okay, so when Einstein developed the quantum theory in the early 20th century, Niels Bohr came up with the quantum atom, the Bohr model of the atom that was refined later with wave mechanics and the and matrix mechanics and so on and so forth. Then Einstein came up with a new form of new means of quantum jumps, a new kind of quantum jumping in atomic orbit, in atoms, electrons going from one atomic level to energy level to another, and that is stimulated emission of photons. So you shine a light of a certain frequency on the atom, and that atom will emit light of a certain frequency, and you can stimulate it essentially. So if you have a gas, let's say argon neon gas, and you do this process, and it can then it can emit very collimated light, and light that is in phase, so that light doesn't diverge out or diffuse out. It stays laser focused, laser sharp. That's why we say laser sharp. So that essentially is laser signals. Are laser signals more effective for future communications? I'm not sure about that. I've not thought about it. um, maybe maybe they could, but lasers are great for focusing energy in a very small beam of light. So you can use lasers for other things like taking down drones and missiles and all that, once you have enough energy. And yeah, that's what is being used these days to take down as anti-missile defense. Okay, let us take one more question. Come on, man. Not this. Okay, let's take this. I was about to take this one. Are chupacabras real? I've seen no evidence of them. Chupacabras. Okay, so there's a question. Xi Jinping ki amma. Do you think India will again lose the race to moon and claiming territory as USA, China, possibly Russia will land their people first on the moon and claim territory? The US is going to land people on the moon in the next year or two. By 26, I believe the first moon landings, return landings will begin. As far as I know, the Chinese want to have people on the moon by the 2030s. The Russians also have ambitions of that. India says we will send a Chandrayaan 10 or 12 or whatever to the moon by 2040 with human beings. So, look, the first mover advantage isn't that big as it is made out to be. Uh, it is obviously a competition, it's a race and all that. But I think claiming territory and all that will happen once you have sufficient people on the moon, which uh, may not need a very significant first mover advantage. Okay. Um, shall we take maybe one more question? Okay, Om Bekerikar has asked, can future events affect the present? What is the delayed choice quantum eraser experiment? If I explain that at this point in time, it will take me at least 10 to 15 minutes, so I will not explain that. But it is an experiment that kind of seems to hint at retrocausality. Retrocausality, which means a future event affecting the present. Means whatever is happening in the present is affected by what's going to happen in the future. That's so weird. It's called retrocausality, and the delayed choice quantum eraser experiment kind of hints at that. But maybe it's not quite the case. Maybe if you investigate it properly, it may not turn out to be retrocausality. So as far as we know, the delayed choice quantum eraser experiment seems to hint at retrocausality, future events affecting the present. But maybe if we investigate properly, it may not be the case. Okay. I'll not explain the experiment right now because it will take too much time. But yeah, great question. Okay, I think we are at the end of today's session, 2 hours, 6 minutes, and whatever seconds. So yeah, I'm going to end it over here. So great to do science, physics, cosmology, all that once again. I'm going to keep on doing this more frequently, more regularly. So, okay, one last question. Manasi says, what's the Higgs boson? The Higgs boson and the Higgs field is that it's a fundamental particle that imparts mass to those fundamental particles that do interact with it. So the stronger a fundamental particle interacts with the Higgs field, the more mass it is, more massive it is, and less and the less strongly a particle interacts with the Higgs field, the less massive it is. Then some particles simply don't interact with the Higgs field, which is why they are massless, like the photon. That's the Higgs boson, and the Higgs boson is part of the Higgs field. Every From the perspective of quantum field theory, there are no particles, it's only fields. And particles are simply local excitations of the fields. So, how many fundamental particles do we have? The standard model 17 plus 17, let's say 17. So, you have 17 different fields that interact in various ways, which give rise to this illusory world that we live in today, this Maya that we live in today. But actually, it's all fields, there are no real particles. That's what it is. Okay, I'm going to end it over here. Thank you so much, everybody, for all the questions. I really appreciate that. I'm going to keep on doing these science sessions as well regularly. So you can expect one next week. So, yeah, that's it for today. I'm going to have a history geopolitics session tomorrow. In case you want to attend that, please do. And hopefully we'll take questions of yours. Until then, thank you for watching. Have a good day, good night, wherever you are. And I'll see you very soon. Bye bye.